Hi, Math 30-1s. Today we're going to take a look at solving log equations. So again, just to review, when we are dealing with equations, remember that at the end of the question, you will have a solution where x, or the variable in the question, equals a specific value, and we can always take those values, go back to the original equation, substitute them into the original equation to make sure they satisfy the equation, which again means the left side of the equation equals the right hand side of the equation. That'll be a very important step today, as you'll see in some of the examples. So in the introduction here, it says there are many techniques for solving log equations. Much of the work will involve using laws of logarithms, so that's your product law, your quotient law, and the power law, so that we arrive at one of the two possible positions shown. Okay, so those two positions that they do show, okay, in the following example, in example 1 here, okay, that's referring to where I have log expressions on either side of the equation and they have the same base. Okay, so as soon as they have the same base, I just basically equate the arguments. That's all I've done there. In the second example, or second situation that we may come across, I've gone from basically log form to exponential form. So b to the exponent of q, which they have here, b to the exponent of q, is equal to your argument, which is p. Okay, and we've done that numerous times in the last couple of lessons. So what for most of the basic questions you're going to see today, we'll arrive at one of those two scenarios, and then I'll show you from there how we get to our final solution. All right, in the exploration, it reads like this. Alice is solving the equation log base 5x plus 1 plus log base 5x minus 3 is equal to 1. Part of her solution, including the explanation, is shown below. And we'll work through that, and then we'll complete her solution. So here's what happens with Alice's solution. In step 1, okay, she notices that she is adding log expressions and she has the same base. Okay, so what that allows her to do is then multiply the arguments together. So she multiplies the x plus 1 by the x minus 3, and you can see that is what happens in the second step there. Going from step 2 to step 3, what happens is she then converts to exponential form. So she then goes 5 to the exponent of 1, okay, which you can see here, equals that argument, which is the x plus 1 times the x minus 3. Okay, so she's converted now into exponential form. So from there, and that takes us to part A, it says complete the solution by solving for x. So all I do from there is I kind of pick up where she left off, which is the x plus 1, x minus 3, okay, equals 5 to the exponent of 1, which is just 5. So I expand those binomials, okay, x squared, then minus 3x plus x minus 3, that equals 5. I will collect my like terms, so this will be minus 2x there. The negative 3, and then I bring 5 across the other side, so minus 5 leaves me with minus 8 is equal to 0. So you'll remember from Math 20 and even Math 10, I have a quadratic here, which is x squared plus bx plus c. So I'm looking for two numbers, or two integers, that multiply to negative 8 and add to negative 2. Okay, those values will be minus 4, okay, and positive 2. So those are the two values that are inside of the binomials. Now, from those two factors, okay, I should be able to determine, okay, that x will equal either 4 or negative 2. Okay, those are the two solutions that come from each of those binomial factors. Okay, so at this point, we're assuming I have two possible solutions, and it worked out relatively easy, relatively straightforward. In part B, though, it says, explain what happens when you try to verify the values of x in the original equation. So I've got two scenarios I have to verify, okay, or check. I have to check x is equal to 4, and then I'm going to have to check x is equal to negative 2. All right, I'm going to have to check each of those individually by substituting them, into the original equation. So this is going to be log base 5 of 4 plus 1. Okay, that goes into the argument, plus log base 5 of 4 minus 3. Okay, that should equal 1. So this will become log base 5 of 5 plus log base 5 of 1. That should equal 1. We know log base 5 of 5 is a value of 1. Log base 5 of 1 has a value of 0. Okay, so I have 1 on the left-hand side, 1 on the right-hand side, and that works. Okay, so x equaling 4 is a variable solution. Now, I go and I deal with x equaling -2, and I do the same thing. So I take my original equation and I substitute in -2. So this is -2 plus 1 plus log base 5 of -2 minus 3, and that should equal 1. So this simplifies to log base 5 of -1 plus log base 5 of 2 minus 3, which is also negative. It would be -2 minus 3, which is -5, okay, equals 1. So at this point, I don't even have to go on with the calculation, because what you can see has happened is when I substitute that solution in, is I end up with negative arguments, okay? And remember, when we are dealing with logarithms, we cannot have negative arguments. So therefore, what that means is that this value is extraneous. We cannot use it. It leads to a negative argument. So the only solution then is x is equal to 4. Okay, this is the only solution that works. Okay, so this equation only has one solution, which is x is equal to 4. Part C says, circle the correct alternative. In solving this equation, Alice arrived at one of the two positions shown at the top of the page, which was in the introduction. The position Alice arrived at is what? Well, she used this law or this scenario to solve the equation, right? She went from log form into exponential form to solve the equation. She didn't have a situation where she had logs on either side of the equal sign that had the same base. Okay, so it was this scenario that she used to solve her equation. Let's turn the page. So it says, when attempting to verify the solution of x equaling -2 in that last example we just worked through, we reach the solution of the log of a negative number. We know that log expressions are, and you can highlight or underline that logs are only defined when we have positive values of the argument. So in that case, like I mentioned on the last page, x equaling -2 was an extraneous solution. And again, an important point here is it's not the fact that x was negative, okay? It's not that x was negative. It's the fact that the value I substituted in made the argument negative, okay? So just because you get a negative solution, don't assume right away that it's not going to work. It's the substitution into the equation, okay, that makes the argument negative, and that's why we can't use it. All right, so taking a look at the next section here. Solving log equations using laws of logarithms. A log expression is defined only for positive values of the argument. Okay, again, same basic idea that we just talked about in the last section, but obviously very important. So we highlight it or note it again. When we solve a log equation, it is essential to verify the solutions do not result in the log of a negative number. Any solutions that would result in the log of a negative number are, again, called extraneous and are not valid solutions, meaning we cannot use them. Values obtained by solving log equations may be extraneous and must be verified. There are two verifications required when the solution is replaced into the original equation. Okay, one, all of the arguments must be positive, and if the base is a variable, it too must be positive. So you will see, and it's not often, but a lot of times the base in your log expressions are also variables. They can't be negative as well. So bases and arguments must be positive when you substitute the values back into the original equations. Okay, so make sure you are aware of those 2 points. Solve the following log equations. First one, log of x squared is equal to log of 16. Okay, so because I have log base 10 on both sides of the equation, I can simply just equate the argument. So I can just say from here, x squared then will equal 16. So x should be equal to either positive or -4. Okay, so I have two solutions I need to verify here. I have to verify x equals 4, and I will do that first, and then I will verify x equals -4. So this will be the log of 4 squared should equal the log of 16, and this is, okay, log 16 equaling log 16, so that solution is okay. I will then work on x equaling -4, and you'll see this is the log of, and this is -4 squared. That should equal the log of 16. So again, I do get log 16 equals log 16. Okay, so both of those solutions do work. Okay, x is equal to both positive and -4. Now I move on to the next equation on the other side of the line here, example 2. So when I have 2 log of x equals log 16, okay, they've kind of used the power law and they moved the 2 that was an exponent by the x from the first example down in front. So now I have 2 log x. So when I go and solve this equation, I could put it back to what it looked like. I could go log of x squared equals log 16. Okay, and therefore I have the exact same scenario I had on the last example. So x should or equal positive or negative 4. So at this point you would assume that both solutions will work because they were very similar calculations, but you're going to see that's not the case here when I go and verify. So when I take x equaling 4, okay, and I substitute, and this is going to be 2 log 4 equals log 16. Okay, that is okay. Now what happens from there, okay, is I can basically do one of two things, right? I could move the 2 in front of the log 4 up to be an exponent. I could change 16 on the right-hand side to 4 squared, bring the 2 down in front. It doesn't really matter, okay? But you're going to see that I go log of 4 squared again equals log 16. Okay, so again, you have log 16 equals log 16. So that one's okay. It's this second one that gives us some trouble. X is equal to negative 4. When I substitute this into the original equation, it's now 2 log of negative 4. Okay, I cannot have a negative argument. So because when I substitute that value in to the original equation and I have log of negative 4, I cannot use this solution. So we call this extraneous because it makes the argument negative. So in the second example, the only solution in this one, okay, is going to be x is equal to negative 4. That's it, okay? X equaling negative 4 does not work. In part B, it says, solve the equations using a graphing technique. Illustrate the solutions on the grids that are provided. So, for example, the first one, let's say that I graph everything as one function. Okay, so I'm going to go the log of x squared, and then I'll bring the log 16 across, so it would be minus log 16. So you'll see what happens when I graph that function. Okay, you get 2 arms that look like this. One there, and another arm that goes up and in this direction. Okay, where when I graph everything as one function, I'm interested in the x-intercepts, and you'll see that when you calculate them, I get x-intercepts or zeros that are at negative 4 and 4, just like I did with the algebraic solution right above it. For the second equation, when I go and graph this one, okay, this would be 2 log x minus log 16. Okay, that graph only produces one arm, which is on the right-hand side of the y-axis, like so. Okay, and you can clearly see that it only has 1 0 or x-intercept at positive 4. So in C, what they logically do is they now ask for an explanation. Okay, explain why the solutions to the log equations are not the same, even though 2 log x can be written as the log of x squared. Well, we took a look at this a while back. I believe it was in the last section of the first chapter we did on exponents and logs, okay? When I take a look at something, for example, that is like this, the log of x squared, okay? Because I'm squaring that argument, the domain for something like that is basically just that x, such that x cannot be equal to 0. That's the only thing I can't have there. Okay? Even if I put a negative number in for that x, I'm squaring it, so it becomes a positive value. But when I take a look at something like 2 log of x, which is the original equation, okay, the domain there is very different, right? We know with log functions that the domain is mostly x is greater than 0. Okay, x is an element of the real. So that's why with the log of x squared, okay, I have the graph that exists on either side of the y-axis. I can use negative or positive x values because I'm squaring them. But in the second one, okay, 2 log of x, I can only have positive values for x because that's what I'm substituting into x, which represents the argument. Okay, so it's the domain restrictions that cause the issue there when we are taking a look at the differences between those two equations. All right. Next page. Solve for x in the following equations. So these are some pretty straightforward equations, very similar to the one that we took a look at on the first page. Okay, so first thing I notice here is that I am subtracting log expressions, and they do have the same base, okay? And even the equation on the other side of the equal sign, or the expression, sorry, on the other side of the equal sign has the same base as well. Those are all good things, okay? Good signs that will allow me to use my laws of logarithms to help me solve. So what I will do on the left-hand side, since I'm subtracting log expressions with the same base, I will divide the arguments. So on the left-hand side, I can simplify this to log base 4 of, and remember the order matters here. It does have to be x plus 1 all over 2x minus 3. Okay, that is my argument there. And on the right-hand side of the equal sign, or of the equation, I now have log base 4 of 8. Okay, this goes back to, again, the first page. I have a scenario where on both sides of the equation, I have logs, and they have the same base, don't they? So what I can basically do from this point is just equate their arguments. So I can say, all right, x plus 1 all over the 2x minus 3 is equal to 8. Now remember, any whole number is actually over a value of 1. That helps me just visualize what I need to do when I'm going to cross multiply now. So that's what I'm going to do, right? Rationals, or rational equations. I'm going to cross multiply there to there and there to there. So I'm going to have 1 times x plus 1, and then 8 times 2x minus 3. So on the left-hand side, obviously, that remains as x plus 1. On the right-hand side, sorry, okay, I got to rewrite this. So here I have x plus 1, and on this side, like I said, 8 times 2x minus 3. So x plus 1 will equal, this will be, sorry, 16x minus 24, okay? I'm distributing that 8 inside that binomial, like so, okay? What I'm going to do now is bring the x's on one side of the equation and the constants on the other. So what I will do, doesn't really matter which way I go, I'll go x minus 16x, like this, on this side, and on the other side you'll have negative 24 minus 1, so you'll have negative 15x equals negative 25. Okay, you're going to divide both sides by negative 15, but you have negative 25, so a negative divided by a negative is positive, and 25 over 15, okay, which you will get here, will reduce to 5 over 3. Okay, so there is your final solution. So the last thing that we basically have to do here is we would have to verify, okay? So what I would do at this point is I would verify that my solution works. And what am I verifying? Well, I'm verifying x equaling 5 over 3, okay? So I have to take that value and basically substitute it into the equation. So what I will get is the following. I'll get log base 4 of, and then you're going to go 5 over 3 plus 1, which will give you 8 over 3. Minus log base 4 of 2 times 5 over 3, which is 10 over 3 minus 3, okay? And when you reduce that, that will give you 1 over 3, okay? Now that has to equal log base 4 of 8, okay? So that has to equal log base 4 of 8, okay? So from there, what we can do with on the left-hand side to simplify is going to be log base 4 of, and then 8 over 3 divided by 1 over 3. Okay, the 3's will cancel, and you'll end up with log base 4 of 8 on the left-hand side, and you get log base 4 of 8 on the right-hand side. Okay, so that value worked. Okay, it satisfied the equation, so we're good to go there. We know that that solution works and is valid. Okay, so x is equal to 5 over 3 in the first question, or in A. Now, moving on to the second equation. Okay, what I'm going to do is something very similar, okay? But what you'll notice here is that I have two log expressions that are on either side, okay, of the equation. So I'm going to bring them together, and I'll leave the number 1 on the other side of the equation. So what I'll do is I'll keep the log base 6 of x plus 4 on the left-hand side. I'll bring the other log expression across, so now it's plus log base 6 of x plus 3. And on the right-hand side, I still have the number 1. Okay, so again, what I have here on the left-hand side is I am adding log expressions, and they have the same base. Okay, so that allows me to, this time, multiply the arguments. So this is going to be log base 6 of, and multiplying the arguments together would be x plus 4 times x plus 3, like so. and that equals 1. Okay, so I have two routes I can go here. I can convert this into exponential form, or I can change the number 1 on the right-hand side to log base 6 of 6 if I wanted to, okay? But I think converting to exponential form will be the easiest here. So what I'm going to do is go 6 to the exponent of 1 equals my argument, okay? Just like we've done over and over and over again. So 6 to the exponent of 1 is 6. That equals my argument. So 6 to the exponent of 1 will equal the argument, which is x plus 4 times x plus 3. So what you end up with here is 6 is equal to, and then I expand these binomials, so you'll have x squared plus 7x, and then plus 12. And then because it is a quadratic equation, I will bring that 6 to the other side, so you'll have x squared plus 7x, and then 12 minus 6 is a positive 6. Okay, so there's the quadratic that we need to factor. So I take a look at factoring that, multiply to 6, add to 7. So that will be x plus 1 and x plus 6, okay, which will lead me to two solutions of x equaling either -1 or -6. So I do have to verify both of those solutions, okay, to make sure that they work. So I will start with -1. I'll do it over here. So I'm going to verify. And this one is x is equal to -1. Okay, so I go into my equation. So this will be log base 6 of -1 plus 4, which will be 3, equals 1 minus log base 6 of -1 plus 3, which is 2. Okay, so that's what we end up with in that case. So what I have to do is, again, I'm verifying, so I can't have things that cross the equal sign. Whatever's on the left-hand side has to stay on the left-hand side. So what I do is I keep this as log base 6 of 3. The number 1, like I said, I can write that as log base 6 of 6 minus log base 6 of 2. So on the right-hand side, subtracting log expressions with the same base, I divide the arguments. So that would be log base 6 of 6 divided by 2, which is 3. Okay, so that one works. Okay, all good. So x equaling 1 is a valid solution. Now I have to go and I have to verify the other potential solution, which is x is equal to -6. So when I go into the equation and do that, I'm going to have log base 6 of -6 plus 4, which is -2, plus log base 6 of -6 plus 3, which is -3, and that should equal 1. Okay, I don't have to go any further because once I substituted that value or potential solution into the original equation, you can see that I have negative arguments, okay, which we cannot have. So therefore, that solution is extraneous. Okay, we can't use it. So the only valid solution in B would be x equaling -1. All right. Third example here. Solve 2 log base 3x minus log base 3 of x plus 2 minus 3 is equal to 0. So what I'm going to do is take this first term, the 2 log base 3 of x, and use the power law, move that 2 from in front of the log expression up to being an exponent attached to the argument. So this will become log base 3 of x squared. Now I have minus log base 3 of x plus 3, and I'm actually going to move that 3, that constant, to the other side of the equation. So now on the left-hand side, I'm subtracting log expressions that have the same base, so I divide the arguments. So it's going to be x squared all over x plus 3, and this equals 3. Now the reason I moved that 3 to the right-hand side is so at this point, this step, I can now convert to exponential form. So 3 to the exponent of 3 will equal x squared all over x plus 3. Okay, so from there, 3 squared is 27, and that's equal to x squared all over x plus 3. So I'm going to cross multiply at this point. And remember, underneath of this 27, okay, even though you don't see it, there is a number 1 there. So this will be 27 times x plus 3 equals 1 times x squared, which is x squared. Okay. So you will have 27 times x, and then 27 times 3, which is 81. That will equal x squared. So I'll take everything to the right-hand side so that x squared remains as a positive term. So this will be x squared minus 27x, and then minus 81. So at this point, you run into a little bit of difficulty, okay, because this quadratic that I have, x squared minus 27, and I apologize, there should be an x there, minus 81, okay, is not factorable using product and sum. I cannot find two integers that multiply to negative 81 and add to negative 27. So unfortunately, what we have to use is our good old friend, the quadratic formula, okay, which if you remember, if you don't, that's okay, I'll write it down. It's always in your on your formula sheet, or it'll be provided for you on a test, but it's x is equal to negative b plus or minus the square root of b squared minus 4ac, and then all over 2a. Okay, so that's our quadratic formula. And if you remember, a is the coefficient in front of the x squared, b is the value in front of the x term, and c is the value of the constant term. So when I substitute those values in, you're going to get x is equal to negative b, which is going to be negative 27. So 27 plus or minus the square root of negative 27 squared. So that's what you'll have under there, negative 27 squared minus 4 times a and times c. So just remember that this radical sign must extend all over that calculation. And then you're dividing all by 2 times a, which is 2 times 1 in this case, which is 2. So when you do those calculations, you will see that you end up with x equaling 29.72, okay, and negative 2.72. So again, two potential solutions. Now, when you take a look at this, I don't even really have to do much with the negative 2.72. It is going to be extraneous. Now, again, it's not the fact that it is necessarily negative right away that I can get rid of it. It's that when I look back at the original equation, there is a variable x, which is a standalone argument. There's nothing else there. So when I put negative 2.72 in there, automatically the argument is negative. I can't use it. So I know just by looking at that original equation right away that negative 2.72 is extraneous. I can't use it. Okay, and again, I trust you guys that you would go through and do this, but 29.72 does work as a valid solution. It's okay. It makes the arguments positive, doesn't make them negative. It makes the left side of the equation equal the right-hand side of the equation. It is a valid solution, okay? So that first part of the lesson, pretty straightforward. Log equations. So the next two questions on the next 2 pages are a little more complex, but again, we're using the same principles over and over and over again, okay? The power law, the product law, and the quotient law, okay, to solve all these log equations. Now, this first one in the section labeled more complex equations is interesting for a couple of reasons, okay? You can see that I have 2 log expressions side by side. Okay, and the other thing I have to be really careful of is that in this question, the base of the second log expression is also a variable. So when I substitute my potential solutions back into that original equation, I have to be aware of 2 things this time, and we mentioned this earlier on in the lesson. I can't have negative arguments, and I can't also have negative bases if the base is a variable, which we have in this case. We haven't seen that yet, but this is the first case of that, or first example of that we're going to take a look at right now. Now, they're nice to you in this question in the sense that they tell you how to solve this one right away. They won't always do that, obviously, but they say convert to exponential form twice. All right, so I'm just going to get rid of what I've written there, and I'll show you how I do this. So first step, convert to exponential form the first time. It's going to be 2 to the exponent of 1, and this is the whole argument, okay, for that first logarithm. So it's going to be 2 to the exponent of 1 equals log base x of 3x plus 4. So there's me converting to exponential form the first time. So I'll just get rid of that exponent of 1. I don't have to write it. It has the same value. So log base x of 3x plus 4. So what I do now is I convert to exponential form a second time. So x to the exponent of 2 equals the argument. So equals 3x plus 4. Okay, so I'll take the 3x plus 4 across to the left-hand side, so I'll end up with x squared minus 3x minus 4 is equal to 0. So pretty quickly you have a nice quadratic equation that you can solve by factoring. And this would become x minus 4 and x plus 1. Those two binomials expanded will give you that quadratic. So from there, we would say, okay, that x is going to equal either 4 or negative 1. Okay, so obviously I have to go and I have to verify each of those. So first I'll verify x equaling 4. So I go to the original equation, so this will be log base 2 of log base, and for that x I put in 4 of 3 times 4, which is 12. 12 plus 4 is 16, and that should equal 1. So this will be log base 2 of, and log base 416 has a value of 2. And then log base 2 of 2 is 1, so 1 does equal 1. Okay, so that solution is good. We can use it. It works. When I go and I use or try to verify the second solution, which is negative 1, okay, let's see what happens. So it's going to be log base 2 of log base, and for x I put in negative 1, and then 3 times negative 1 is negative 3. Negative 3 plus 4 would be 1. Should equal 1. But again, the issue is this, that when I substituted that value in, this time I ended up with a negative base. Okay, so therefore that solution is extraneous. I cannot use it. So in this equation, the only valid solution, okay, is x is equal to 4, negative 1 extraneous. We cannot use it. Okay, so again, be careful of that. That's your one look at where it makes the log expression of a base negative. So extraneous solution cannot use it. All right, last question. Now this last question takes a couple minutes. It is a little bit longer just because there's different parts to it. But you will run across or see a couple of these questions in your homework. They don't appear a lot, but you will see them. Okay, so it reads like this: solve and verify. Solve the equation log of x squared minus 3 log x equals 10 using the laws of logarithms. Okay, so what I'm going to do then, if I'm using the laws of logarithms, I'm going to take this exponent, move it down in front of the log expression. So 2 log x minus 3 log x equals 10. So if I have 2 log x's and I'm subtracting 3 log x's, I have negative 1 log x. Right? I'm subtracting the same thing. I just have different numbers of them. 2 log x's minus 3 log x's is negative 1 log x's equals 10. Now, if I want to basically figure out what x is, I'm going to divide both sides by the negative that is in front of the log, like so. Okay. Now, at this point, okay, do not forget that even though you don't see it, there is a base 10 here. So that allows me to convert to exponential form. So this would be 10 to the exponent of negative 10 is equal to x, okay? And, you know, they might rewrite it a different way if you looked in a different book. This is 1 over 10 to the exponent of 10 equals x, okay? Something along those lines, okay? So there is your solution, 1 over 10 to the exponent of 10, okay, or 10 to the exponent of negative 10. If I verify that, okay, it does work, okay? So it does check to be a viable solution. It is does satisfy the equation, okay? It does make the left-hand side equal the right-hand side of the equation. To do that, just go 10 to the exponent of negative 10, substitute that into the x's in the original equation, and you will see the left side does equal the right side of the equation. So in part B, it says, explain why the equation log of x squared minus 3 log of x can't be solved using the laws of logarithms, okay? And the key reason is the following. When you see this, the log of x squared, okay, that is not the same as in part A where I have the log of x squared. So, you know, just on the side, you can say, well, the log of x squared is not the same as the log of x squared. Those are not the same thing. In the first one, you're squaring the argument. In the second one, you're trying to square log x. Those are very different things. Okay, so I cannot go and solve it the same way. So it's only when the exponent, I apologize, is attached to the argument. not defining or attached to the whole log x expression. Okay, so that's why we can't do it. You can't use the laws of logarithms, specifically the power law, when that is the case. So in part C, moving on, you're going to see how to solve those types of those types of equations where the whole log x expression is squared or cubed or, okay, whatever. So what they say here is replace log x by a new variable, and that variable that they are going to use is a. Okay, so here's what's going to happen. I think I'm going to rewrite this out so that I can kind of follow it a little bit better through the notes here. So I have log of x, it's all squared, minus 3 log x, and that equals 10. So what they're saying is replace log x with a. So here I have a log x, and here I have a log x. Those are going to be replaced by the variable a. That's what they want me to do. So if I do that, what I end up with is a, I still have the squared, minus 3, and then the a, that equals 10. So solve for a. Well, what I really have here is a quadratic, right? So I'm going to go a squared minus 3a, bring that 10 across, and it equals 0. So when you do that, you can factor it. So this will become a minus 5 and a plus 2. Okay, numbers that multiply to negative 10 and add to negative 3. So in this case, you would say, okay, a is equal to 5, or a is equal to negative 2. Right? That's what you've found. But remember, a was not originally a. A was log x. That's what I replaced it with. So then you would say, okay, well, therefore, what that means is log x actually potentially equals 5 or negative 2. So what I have to do is now solve for x, right? Because I have log x equals those values. They want you to solve for x. Again, do not forget that we have a base 10 here. That's going to basically allow me to figure out what x is in each of those cases. So if I go log x equals 5, well, that would be 10 to the exponent of 5 equals x, okay? And as a number, that's 100,000. Okay, so there's the first one. Now, the other one would be log x equals negative 2. So 10 to the exponent of negative 2 equals x. So that's 1 over 10 squared, which would be 1 over 100. Okay, and that is the second value of x. Now, when you go and you verify those, okay, you'll see again that those both work. Okay, so I'm spending less time on verifying, okay, at this point. I'm assuming at this point you guys are able to substitute those values into an equation, see if the left-hand side equals the right-hand side of the equation, and double check that those values or solutions do not make either the bases of the logs or the arguments negative. Okay, so that's how we deal with questions like that. And like I said, you will see a couple of those in your homework assignment. Now, last part here. It says a student is solving the log equation, log of x, and notice the whole thing is squared, minus log x cubed equals 0. Her work is shown. So what this student does, okay, is she says, okay, very similar. I'm going to let a be log x. So she goes a squared minus a cubed equals 0. Then she factors out an a squared, leaving me with 1 minus a. So then she says, okay, well, either a squared or 1 minus a has to equal 0. So she figures out a is 0 or a is 1 and remembers that, well, a wasn't a was actually log x, just like we did in the last question. So log x equals 0 or log x equals 1. The base that you don't see is 10, so 10 to the exponent of 0 equals x. 10 to the exponent of 1 equals x. So 1 and 10 are my solutions. Now, there is an error in the student's work because x equaling 10 does not satisfy the original equation. What's the error? And then provide the correct solution. Okay, so what the student's error is, okay, is the following. She's okay in her assumption where she lets a equal log x. So where I still have that blue check mark, that's okay. The error here, though, is when she lets the second term equal a cubed, okay? Because a represents log of x. This cubed is not being applied to the whole log of x like it is in the first term. Okay, so that's the error there. You can see that log of x is all squared. Log of x is not all cubed, so I can't simply just replace it with that. So here's what I'm going to do. I'm going to start with the same thing, okay? So this is okay. I'm going to let a equal log x. So what that would mean is log of x squared, but for the second term, I'm going to bring the 3 down in front. So I'd have 3 log x equals 0, and we just said log of x can be replaced with a, so this is minus 3a equals 0. Okay, so that's what the student should have done. Now they can kind of do the similar process, factor out an a, and that will leave me with a minus 3 equals 0. Okay, so in this case I could say, all right, well, either a equals 0 or a minus 3 equals 0, which means a is equal to 3. But again, a was not a was log of x, right? I did that replacing up here. A is actually log x, so I would have log x equals 0. And here, sorry, that's a terrible 0. Okay, log of x is equal to 0. And here I would have log of x is equal to 3. So again, converting to exponential form, this would be 10 to the exponent of 0 equals x. Okay, so that's 1. Here, 10 cubed is equal to x, and that is 1,000. Okay, so verifying those solutions, you will see that they both work. So that is the correct method and correct process to solving that equation. So 1 and 1,000 are both correct solutions, no extraneous solutions, and that's the end of that lesson. Okay, so take a couple, a day and a half to work on those. Make sure you're okay with them. I'll be back tomorrow with the final lesson of exponents and logs. So please make sure you're checking the Google Classroom, which I'm sure you are if you're listening to this video, and you're aware of the upcoming evaluation, which is again on both sections, both chapters of exponents and logs. All right. Any questions, as always, send them to me. I'll get back to you with solutions, helpful hints, those kinds of things. Have a good night, you guys. Talk to you soon.